Hello, everybody. All right, so I'm going to help talk with you and kind of go through this to help you out about what waves tell us about the inside of the Earth. So we learned about the different layers, we learned about their densities, we learned about the temperatures. How do waves tell us some of this information? So first of all, I want you to note right here, seismic waves. You might want to highlight that, underline it, circle it. So if you don't have a highlighter, grab one or a colored pencil. So seismic waves is another word, or another way of saying earthquake waves. And this is energy that can travel through the earth. We know that earthquake waves start from tectonic plates moving around. And so this energy then transfers all around the crust and then down in through the layers. So what evidence do we get from earthquake waves to tell us what the inside of the earth is like? So let's go through. There's a few pieces of information, and I want you to kind of pay attention to the main details, and I'll help kind of explain it. Okay, the first piece of evidence, and I'm going to highlight this, and you probably should too, is that waves refract inside of the Earth. That's a wave behavior. We've talked about this before, and I showed you guys the pencil inside of the tub of water. When you have that pencil in there, you see that it's kind of offset looking, even though the pencil hasn't changed. Well, remember what's happening is that the waves are traveling through the air, and then they hit the water, which has a different density, and it changes how the waves behave, and it bends their path at a different angle. So let's see, what does that mean? I just kind of explained. Refract means that the waves travel through and they go at a new angle. That's what the earthquake waves are doing. So the earthquake happens and the waves start to go through the layers and boom, it hits another layer. Well, what does that wave do? It bends its path and it curves its path and kind of makes it travel in a different direction. Now you'll notice in the picture, you'll see it's kind of just curved. Well, the density is constantly increasing throughout a layer as well, so it's not the same density the entire depth of that layer, so the wave is constantly changing its little path. So why do the waves refract inside of the Earth? It's because they hit that new layer with new density, as I said before. That's really going to be the huge theme about all of these different pieces of data, is that they hit this new layer with a different density. So if you look at this picture, and I made a mistake. You see that here is where the earthquake's epicenter is. Womp womp. So I made a little boo-boo on my picture. Remember, epicenter is the origin of the earthquake on the surface, because the focus is where that earthquake happens deep inside the earth, but the epicenter is where that happens on the surface. So I instead made my little star here, and that's just a different epicenter. But you'll see that as it goes through each layer, the path of the wave is bending. So make sure, pause it if you need to, and sketch this picture because you're going to see something similar to that in the future. All right, so that's first piece of data, refraction. All right, now on the inside, I gotta move myself. Whoa! Okay, the first thing is, on this section is that waves reflect inside the Earth. I would highlight star, make that stand out. So waves don't just refract, they also reflect. What does that mean? Well, we saw with our slinky that the wave bounced back. And it's the same thing like in a mirror. You have a reflection because the light waves are coming in, they hit the mirror and they're bouncing back. And that's how you can see something in a reflection, because the light is bouncing off of it and bouncing back. Well, earthquake waves do the same thing, just like sound waves. An echo is a reflection. So the waves are bouncing back. So why? Oh no, I didn't write this down. Silly me. Why do waves reflect inside the Earth? But you probably guessed because I said that is a major theme. And it's that they hit a new layer with a different density. So I don't have that typed out, sorry, but you can write that down. They reflect inside the Earth because they come to a new layer and they bounce off. And they go in a backwards or in kind of a different angle off of that layer. So in my picture, and again, I made a mistake. I should be more careful. Sorry. You make sure you do it right, though. Or you can copy mine. It's fine. It's the same idea. If this was the earthquake epicenter, that's the origin of the earthquake, then if you see how my mouse is going, it would be bouncing off like that. Instead, I've chosen to start my earthquake down here at a different point of the Earth. Same thing. The earthquake wave travels, the seismic wave travels, it gets to this layer, and it bounces off. Same thing on this side, because technically waves are going in all directions. So I'm just doing a couple arrows. It's happening, though, consistently throughout. It's called propagation. The wave is propagating. It's propagating in all directions. All right, so the next piece of information that tells us what the inside of the Earth is like is this. And it is super important that S waves don't travel inside the outer core. They stop. So you should be writing that down. What does that mean? It means that the S waves stop at the outer core. And that's my secret little hint to you, is that S for stop and S for S wave. It's an easy way to remember it. And don't worry, we'll talk about it in class. I'll probably come up with a stupid chant for it, so get ready. All right, so the outer core is a liquid. We've talked about that before. It's liquid iron. It's got some other metals in there, but mostly liquid iron. And the S waves can't travel. They're transverse. They can't travel through that liquid. So my picture, and I did it right this time, here's the epicenter. The earthquake wave goes, and boom, it stops. It can't travel through. That's a huge piece of information about that, about the outer core, because as we're reading all those seismograph information on the outside of the Earth at different locations, they're not getting that secondary, the S wave is the secondary wave. They weren't getting that S wave based on how you would expect the path of the wave to travel, and it's because the wave just stops. It can't continue. All right, last but not least is this silly graph again. Oh, there it is. I told you to be able to read that and understand it. You're going to see this idea throughout the rest of our unit. But here's the reason we have this graph, is that the wave speed is different throughout the layers. And I'm going to, move again. So the wave speed is different throughout the layers, and we did this in that Speedy Waves lab. We took those tuning forks and we saw that when we held it in the air and when we put it down on the table and listened, that the waves were traveling differently through the air versus the table. So why does the wave speed change? Whether it's sound or earthquake waves, it has to do with the different densities. And waves travel faster in a more dense material. So that's the important understanding of this whole part of the unit. Its density is kind of creating all these different conditions for the waves to behave differently. All right, so here's our graph. There we go. All right, so we've got this graph. We looked at it in class. We looked at it on the lab, the Speedy Waves lab, so you kind of should be familiar with this. So what does this tell you? When we look at this, it tells us that the P waves are faster than the S waves. I'm going to move this, sorry. But if you look up here, this is our wave velocity. Oh, no, that's not it. What are we highlighting here? Oh, because it's a picture, that's why. All right, well, ignore Earth explained. But if you want to highlight wave velocity up here on your paper, do that. Wave velocity is getting faster and faster and faster and faster the farther right we go. So if we look, then the P waves are farther right, and so it's indicating that they are faster. The P waves can go through the liquid outer core. You can see down here that they're able to travel through. However, remember, their speed decreases rapidly because they're behaving a little differently in that liquid. But they do get faster in more dense material because even that way up here, it's getting more and more dense as you go through the mantle, the waves get faster. It's getting more and more dense as the depth of the outer core increases, they get faster. And the same thing for the inner core. Now, S waves are the secondary waves. These are the second ones to come out of the earthquake. They are slower. And they cannot... Oh, sorry, that's probably annoying. That little... Well, now you know where the picture came from. But they cannot go through the liquid outer core. They just simply stop. You can see that right there. They're done. They can't travel. Their energy doesn't continue to propagate. But they also get faster in more dense material, which is indicated by this is moving. It's not quite as maybe as steep as, or it looks a little more steep. It's not moving as much as the P wave. But as you're going further and further right, the speed of the S wave increases. All right, so we've got 4 main pieces of evidence that you need to know about that tell us what the inside of the Earth is. 1, earthquake waves refract. 2, earthquake waves reflect. 3, S waves cannot go through the outer core because it's liquid. And 4, as waves go deeper and deeper into the center of the Earth, they're going to go faster and faster as the layers get more and more dense. Now remember that outer core is kind of tricky business, and the speed does slow down, but it's not slowing down because of the density. It's slowing down because of how the mechanics of how the wave is working through the liquid. Okay, so good job with that. If you need to go back and pause the video anywhere and get it all copied down, get that down, and think about those 4 main pieces of evidence and how the Earth is telling us about itself using the earthquake waves. That was an awful exit. So anyway, just you can skip this part and have a good day.